Oh, sorry, I was on mute. So I guess we have some attendees and welcome all of you to, this is what, fourth day, fifth day? This is the fifth day, I think. Yeah, it is. So it's been a wonderful week as well. And thank you so much all to join up for such a big event and supporting us, supporting all of us and supporting the Slack channel as well. And, constantly interacting with all of us. Thank you so much for all of this. And today we have Dr. Promit Ray, who is a data scientist working at Atheneum. And he will be displaying to you and talking to you about SVM, that is support vector machine. Over to you, Promit, and you can start sharing. I believe you should have the option to share the screen. Are you able to share it?
I'm trying.
Yeah.
Is my screen visible?
Yeah, it's visible now. All the best, Promit.
Awesome. So hello. Thank you, Soham, for that lovely introduction. And hello, everybody. Really happy to be here. And thank you for joining. Let me go ahead and start presenting my screen. All right. So hello, and depending on where you're joining from, good afternoon or good evening. Welcome to block 4 of this marathon, Machine Learning Made Simple. Today, I'm going to speak about introduction to support vector machines and of this module. Tomorrow will be the hands-on version. I thank Soham and Newton.ai as co-organizers, as well as all the other partners, AI Guild, Bell Integrator, Silicon Valley for You, and PACT. It's been a wonderful, wonderful event, loaded with information, and I'm really excited to be here and speak to all of you. Today's session is going to be on introduction to support vector machines. So like I said, today is part 1, where I'm going to talk about conceptual and the mathematical framework of support vector machines, classification and regression using support vector machines, and then some examples of coding that can be done through support vector machines. Tomorrow, I'm going to do some live coding along with you. So I hope to see you there with your computers. I'm going to run all code on Jupyter Notebook. I'm going to tell you during the course of the presentation what examples we are going to work on. So you can come with some preparation if you like. But if you just want to come and watch me code, that is, of course, fine as well. Before I begin, I wanted to give you a short introduction of myself. I studied in Bonn. I did a PhD in computational chemistry before moving to the data field. I worked for 2 years prior to this for a digital healthcare firm in Berlin, and have now moved to Atheneum, which is a strategy consulting firm. Atheneum is also based out of Berlin. They're a knowledge sharing platform, and they do strategy consulting and global business intelligence. I'm a data scientist for them in the data engineering division. And with that, let me introduce the talk. So I'm going to speak about support vector machines. So the first part will be introducing support vector machines, before which I'll first set the foundation for introducing support vector machines. And then I'll talk about the motivation for the methodologies used in support vector machines. And then I'll talk about classifiers and regression based on support vector machines, and then some representative examples and industrial applications of SVMs. So the speakers before me have done phenomenal jobs, and at this point, you should be more than familiar with the general buzzwords and the nomenclature within this space. But for people who are just joining today, and also for the sake of completeness, I thought I will start with this. So the basic buzzwords within this field can be represented by concentric circles, which is what I've done here. So artificial intelligence is the overarching field, which is a simulation of human intelligence by computational rationality. So basically mimic human intelligence with a machine. A subfield thereof is machine learning, where programs can learn autonomously without being explicitly programmed. And deep learning is then a subset of machine learning, in which artificial neural networks adapt and learn from vast amounts of data. So this is the general diagram, and machine learning is the circle in the middle. So a question that often comes up and often also sets the stage for these discussions is trying to differentiate normal rule-based programs from machine learning-based models or data-driven models. So if you have a normal program, you'll have a data source with some sort of input, and you'll explicitly program a rule that will then give you an output. When you go for a machine learning approach, what you do is you take your data into a learning algorithm, which you adjust using your hyperparameters, and then you get a model with certain model parameters that reads in new data and makes a predicted output. So the machine learns from the data, which is why it's called machine learning. There are three main fields of machine learning. The first one, and the one that we're going to talk about today, is supervised learning, where there's clearly labeled data that the machine can learn from. So the machine just has to learn the relationship between specific inputs and outputs and human feedback. The two types of supervised learning applications are classification and regression, and both are possible with support vector machines, and I'll be speaking about both briefly. The second type is unsupervised learning, where there isn't clearly labeled data. So the algorithm looks for trends and patterns without a specific output variable. Examples of this type are clustering and dimensionality reduction. Reinforcement learning is the third type, which is state of the art. The algorithm learns over time to maximize returns based on some reward. Examples here are gaming, finance sector, robots, particularly common in the trading space. This is work in progress, and there are new applications coming up in the space on an everyday basis. Before I start talking about support vector machines, I want to point you to some excellent resources, because of course, an extensive discussion of everything is not possible in the time that I have today. More importantly, I've also taken material from these sources. I will later share it in the Slack channel as well. The first one is Python Data Science Handbook by Jake van der Plas. Highly recommended, excellent section on machine learning algorithms in general, but also very nice illustrations on support vector machines. There is an excerpt from the book on GitHub, and there are also illustrative Jupyter notebooks that you can play with and work your way through the concepts. I've taken some material from there. Chapter 9, Introduction to Statistical Learning, takes you through all the mathematics that you need to set the foundation for support vector machines. Other than this, I've also taken material from online resources, articles in Towards Data Science, Analytics Vidya, and Medium publications in general on the field. All right, before I start, a quick note to participants. I will stop and look at the chat box at regular intervals just to make sure that A, you're keeping up with me, and B, that we can keep this interactive, because I don't want to keep speaking for an hour continuously without hearing from you. So please interact with me in the chat box, ask questions. If you have comments, please put in your comments. The panelists will try and answer if they can, but I will look at the questions on a regular basis as well. So let's start with support vector machines finally. So like I already told you, they are supervised learning models for classification and regression analysis. So it's quite an old algorithm in its original form, at least. It was invented in 1963 by Vladimir Vapnik, who is the pioneer of this field. The present implementation, however, was developed at AT&T Bell Labs, also by these people, but there were other people who contributed. The present version contains a soft margin, estimator addition, and also a method to deal with nonlinear data sets, basically by the use of kernelization. And these publications basically introduce these methods as well into the original algorithm. So what actually happens in a support vector machine algorithm? So what you're basically trying to do is create a gap between two classes. So the algorithm maps training samples to points in space so as to maximize the width of the gap, so that the demarcation between the classes becomes absolutely clear and unquestionable. So the algorithm can then decide based on the location which class a new data point belongs to. So basically, that is what the slide is telling you. New samples are mapped and predicted to belong based on which side they fall. In case you don't have labeled data, then you'd have to go for an unsupervised learning algorithm, but you can use the same principle then. It'll just be called vector clustering. And that also works really. All right. So now let me try to talk you through the intuition behind support vector machines, and hopefully this will be interactive and you can actually follow along. Let's take a very simple example where I have a two-dimensional space and a randomly clustered points. Just to make it really simple, to take the argument forward, I've separated my points really well. Real life data is seldom like this. I've also stuck to 2 dimensions to make sure that we can easily work through the concepts. Now, my aim is very simple. I want to separate the 2 categories from each other. And this is called discriminate classification. I want to find a line, a curve, a manifold, a hyperplane, whatever you like to call it, to separate the 2 classes. Tell me in the chat box, what could I do? What can I do to separate the 2 classes? Nobody? Yeah, that's a good option. Anything else? All right, let me move forward. Yes, indeed, you can draw a line in between. So what I was basically asking is, what can I do to separate the 2 categories? What kind of a line can I draw? So you're absolutely right. You can draw a line in between the 2 classes. Now, the question is, which line would you draw? All these 3 lines separate the classes perfectly. But there is one important consideration. Depending on which line you choose, the new point X could be labeled as a blue point or as a red point. So for instance, if I go with the green line, then my point X belongs to the red category. Do you see that? Whereas if I go with the orange line, then my point X belongs to the blue category. And if I go with the blue line, my point X also belongs to the blue category. Yes, the line has to be equidistant from both classes. That's a very good point. Thank you. Thank you very much for saying that. Yeah, so depending on the choice, X will be assigned a new label, which really does not work for us, does it? And so we have to think harder. What can we do? We can add a little twist to the concept that I had previously described. What we can now do is we can build a little margin around each of the lines to make sure that the margin goes and touches the classes at some points. So both the classes have to be touched at certain points. So now if you look at the gray margins for each of the lines, you will see that the width of the margin varies so that each of the boundaries actually go and touch the respective classes. And what is clear from this is that the different lines would have to have different margin widths around them so as to define boundaries which can touch the points from each of the classes. And so what we try to do in support vector machines is to maximize the margin. So we try to go with that boundary which gives the maximum width of the margin so that the points can be clearly demarcated. So how would this look for the data that I just described? If you put these data points into scikit-learn, which is a Python package for machine learning, what would you get using a linear kernel? I'll talk to you later about what a kernel is, but for now, all you need to know is that the data points are linearly separable, as you can see, and this is basically the point that you arrive with. And so what happens is this is the hyperplane, or the line in our case, which gives you the maximum margin. The orange line here is the demarcating line, which maximizes margin between the two sets of points. And in green are the points from each of the classes, which represent the bounding condition. And the yellow line and the points labeled in green are then called the support vectors. Support vectors are really, really important, and that's how the algorithm is named, because they are pivotal in describing your hyperplanes, which demarcate your two classes from each other. This then directly takes me to the terminologies that one uses in support vector machines. So support vectors are points on either side closest to the hyperplane. And these points define the margins. And what we're trying to do is maximize the margin. Then the next thing that you'll often hear in the context of support vector machines is hyperplane. So hyperplane, in case of two-dimensional data sets, this is just a line. If you have higher dimensions, then you would have a hyperplane separating the two classes. And so this, the one in between, will be a maximum margin hyperplane. And on either sides, you'll have positive and negative hyperplanes such that this hyperplane is equidistant from the other two. And the other two hyperplanes will, of course, contain the support vectors. So you have a maximum margin hyperplane, a negative hyperplane, a positive hyperplane, and a maximum margin in between the hyperplanes, which define your setup for support vector machines. Are there any questions so far? All right. If not, then let's talk a little bit more about how support vector machines actually work. So what we want to do is segregate the data set in the best possible way. So we will select a hyperplane with the maximum possible margin between the support vectors. So here in this diagram, my support vectors are shown here and here. In the case of this category, there are actually two support vectors. What often happens in order to get a really good fit for the available data, there will have to be some points which are misclassified. And this is what I wanted to show here in the diagram. So actually, this point here is misclassified. This point here is misclassified. You see why? What should it actually be? So these boundaries should define your two classes clearly. So typically, I should only have squares on this side. So if I have the category square on this side, this is misclassified, and the same then for the circle here. Of course, as I said, you need a maximum margin between the two classes, and that is what we're going to now talk about in the next section. So what do I need to do then to find the optimal hyperplane for my data? How do I segregate my data in the best way? So this is a three-step process using which I'll walk you through the mathematics of the model. Trying to keep this at a very basic level. I've tried to tailor this talk for a general audience, but at the same time go into some mathematical details. So I hope you can follow. And if there's anything that is not clear, please do interact with me in the chat box. We want as much interaction from the audience as possible. And so I'd love to hear from you. In the first step, what I'm going to do is I'm going to represent the initial data set that needs to be classified. Understand how it looks. We'll talk about set theory notation a little bit. Then I'm going to select two hyperplanes, decision boundaries that separate the data sets. But as I showed you, just any hyperplane or boundary that separates the data sets isn't going to work. I have to find my optimal hyperplane. So I'm going to maximize the distance between the two hyperplanes and show you how this is done, and then arrive at the perfect optimal hyperplane, which will define my support vectors in such a way that the classes get clearly separated. All right, so let's look at a typical two-dimensional data set once again. You can have complexity arising from the distribution as well as dimensionality. So if you have non-linearly separable data, none of this is going to work. And we have to apply a trick on top of everything that I'm telling you. But the trick comes later, basics first, right? So let's look at linearly separable data that looks like this. So my data is going to be composed of n vectors xi, each point associated with a label. And the label is binary in this case, so I can call it plus or minus 1. So y is going to basically belong to either -1 or +1, this category here. And the vectors themselves can belong to a p-dimensional space. So each of these vectors will have p dimensions, and there can be n vectors of this kind. So this is my space. And linearly separable data can be separated by a hyperplane, and we are now looking for this hyperplane. So let's go ahead now and select two hyperplanes. Let's find two hyperplanes with no points in between. So back to coordinate geometry, how do I write the equation of a hyperplane? So any hyperplane can be written as a set of points xi satisfying w dot x, this is an inner product, minus b equal to 0, where w is the normal to the plane, x is your vector points which are satisfying this equation, which are on the plane basically, and b is your offset parameter. If this hyperplane can separate the classes, then hyperplanes which are shifted parallelly by a certain amount can also satisfy this condition, right? So I can have a parameter delta instead of 0, and this would still work. And likewise, minus delta. Delta in my case is totally arbitrary, so I can call it 1 instead. So I can also have these two hyperplanes shown here, which separate the points perfectly as well, as will a hyperplane in between, which would be this hyperplane, which is not shown in this diagram. Is this clear? So what constraints apply then? Can we select any hyperplane? So let's look at the constraints that these points would have to satisfy, and with respect to the hyperplanes. For each vector xi, w dot x minus b greater than or equal to 1 for xi belonging to class 1. So for all points which lie on this side of this line, this will be greater than 1 because the support vectors will satisfy this equation, and all points which lie on this side will then satisfy the condition that w dot x minus b is greater than 1, and equality is achieved in case of the support vectors. By a similar logic, one should be able to see that if xi belongs to class 2, which is the blue category in this case, then w dot x minus b is less than or equal to -1, and equality once again will be achieved for point h, which is your support vector. If this is clear, then let's try and understand the constraints a little further. Here I've defined the hyperplane slightly differently, or depending on how you look at it, define the distribution of my points slightly differently. So now, please tell me which points will not satisfy the constraint for the red class anymore. For class 1, which points will not satisfy the constraint anymore? So points E, G, and F lie on this side of the line, and the other points lie on this side. So please tell me which points will not satisfy the condition, and the same for blue. A, C, D, and B. You say A, C, D, and B. Excellent. Yes, indeed. A, C, D, and B are now on the wrong side, so to speak, of the line, as is point H for the blue category. Yes, absolutely. Thank you for the answers. Very nice. Very nice. And therefore, there are some points which are now correctly classified and some which aren't, and the same goes for the blue points. So hopefully, you're now able to understand what I mean when I say the constraints are obeyed or not, and we will now move ahead. Okay, so let's look at this equation again. I said w dot x minus b is less than or equal to -1 for the blue points, right? But here, my point is labeled as -1. And so if I multiply both sides of the equation with yi, the sign will change because yi is -1. so my sign changes and I land up with yi times w dot x minus b is greater than or equal to 1, right? Likewise, for points belonging to the red category, which in this case is labeled 1, what I will have is w dot x minus b is greater than or equal to 1, and here y is equal to 1, so nothing happens. I mean, the sign of the equality doesn't change when I multiply by y, and I land up with yi times w dot x minus b is greater than or equal to 1. The point is that these two equations are identical to each other and therefore define a unique constraint for no points to lie in between the hyperplanes. And this is what I'm trying to show here. So if I have a set of vectors represented in this way, this is the condition that makes sure that there are no points in between the hyperplanes. And these are the constraints that I have to obey to make sure that my hyperplanes are clearly separating my classes with no points in between. All right, so I've managed to now find two hyperplanes to separate my classes, and the third hyperplane is then in between. So that works out perfectly. Now I need to find the hyperplane. And what is the hyperplane? The hyperplane with the maximum margin. So the maximal margin estimator, so to speak, which is the basis of the SVM algorithm, is what we are now going to do. So once again, we have w dot x minus b equal to -1, which is the h0 hyperplane, and we have the h1 hyperplane, which is w dot x minus b is equal to 1. So one is w dot x minus b is -1, and the other is 1. And m is now the distance from perpendicular distance from x0 to hyperplane h1, which basically means that this is the distance between the two hyperplanes. And optimization of the parameter m is the same as maximizing the margin. Now, one might think that if I add m to x0, I will arrive on the plane h1. Is this correct? If I add m to x0, the margin m to x0, will I land on the plane h1? Yeah, so you people are saying, yes, that's how it looks, right? I mean, if I sit on h0, on x0, which is on plane h0, and add m, I will land up on h1. No, absolutely not. This is not how it works, because x0 is a vector and m is a scalar at the moment. M is just the margin. I have to transform m into a vector that I can add to x0, and then I can actually land up on h1. So to make this clearer, let's ask the following question. What are the points that at a distance of m from x0? So if you look at this, and I draw a circle with radius m, basically all the points that lie on this circle are at a distance of m from x0. But only one of these points actually lies on h1. And how am I going to find this? By using the condition that this has to be perpendicular. So the necessity of vectors hopefully becomes clear from this example. Just having a magnitude of m doesn't work. It has to be perpendicular to h1. So the target vector that I'm looking for has a magnitude of m, but is perpendicular to h1. How am I going to do this? Well, I already know a vector that's perpendicular to h1. In its very definition, w dot x minus b equals 1. W is the normal vector. So if I divide the vector by its magnitude, I get a unit vector in this direction. And if I then multiply it with m, then that is the vector that I want. That has a magnitude of m because I multiplied it by m. The rest is just unity because it's a vector divided by its modulus, but it is in the direction that I want, in the same direction as w. Hopefully this is clear. I'll give a moment for this to sink in. All right. If if this is clear, then let's go to the next step. What have I got here? So I had point x0, and now I found my vector k, which has a magnitude of m, but is in the right direction. And this now takes me to the point z0 on h1. So z0 is now x0 plus k. This vector can be represented as the sum of these two other vectors. Z0, however, lies on h1, and so it satisfies this condition w dot z0 minus b is equal to 1, which is the equation of the hyperplane h1. Z0, however, is x0 plus k, and we put in k as computed in the previous step. And basically what this then gives you is this equation here. W dot x0 plus m into modulus of w minus b is equal to 1. W dot x0 minus b is nothing but minus 1, because that is the equation of h0. X0 lies on h0. And so what I get is m into modulus of w is 2. And if you didn't follow anything so far, then I would like you to take away this. M into modulus of w is 2, which basically means that if I have to maximize my margin m, I could also try and minimize the norm of the vector w. And that is basically what we're trying to do. And that is how the margin is computed. So now we talked about points that are linearly separable and how you would be able to compute the margin and therefore maximize the margin by minimizing the norm of the vector w, which gives you a hyperplane that separates the two boundaries. An underlying assumption that I made, however, was that the points are linearly separable. What happens if the points are not linearly separable and they look like this? So now I'd like you to engage with me in the chat box, please. I have points belonging to two classes. I have yellow points and red points. What is pretty clear here is that no linear discriminator will ever be able to separate this data. So what would you do? What could I do? Any ideas? Kernelization, if it's not linearly separable, we try to increase the dimensions. Exactly. Thank you. So this is the point at which I want to enter the domain of kernelization. So we project the data into a higher dimension to make it linearly separable. And this is nonlinear classification. Exactly. So the principle here is basically called kernelization. And let me quickly explain from a very, very, very basic perspective what kernels actually are. And then I'll show you how it looks for the points that I brought up in the previous slide. What happens if we are unable to find a separating hyperplane in a given dimension? What I could do is project it onto a higher dimension, as is shown here. And then I can very easily find a plane that separates the 2 points. This should be clear. But what is also probably and hopefully clear is that I have to come up with the right sort of projection to make sure that I can put a hyperplane in between to separate the data. For instance, here, the radial basis function is centered around the red clump. And this allows for the data to be perfectly separated. So what we're basically doing is we're increasing the dimension, which requires increased computational cost. What kernelization helps you do is find a higher plane in in higher dimensions, fly, and it gives you a boundary that looks something like this. So it maps the feature space to a higher dimensional space and gives you the corresponding hyperplane and maps it back to your existing space. And this is basically what is shown here. So this is your kernel functions, and usually m is much larger than n for this to make sense. So what f is basically doing is taking your n-dimensional space and converting it into an m-dimensional space. However, since you're taking an inner product, you get a scalar anyway, and dot product by first going to a higher dimension space and then coming back, it would be much more efficient. And this is the concept of kernelization. So let's go back to the points that I described earlier. So if I now take this kind of a Gaussian radial basis function centered on the middle clump, the yellow clump, then of course I see that it looks very nice. And I can very easily define a hyperplane at r equal to 0.7, let's say, which will trivially separate the points. They become linearly separable. But the point here to note is that centering the basis functions in the right location is crucial for this to work. One possible way around this could be to compute a basis function centered at every point and let the algorithm choose. In this case, I knew that I had to center it at the yellow clump to make this work. But when you're running the algorithm, how would you make this work? So of course, you could do this for every point that you have and let the algorithm sift through your results. Or you could do a kernel transformation, which does a fit on the transform data implicitly. As I explained, you don't need to build the full n-dimensional representation, and therefore you can very easily visualize your boundaries in this way. So here, the boundary that will actually separate the points is a circular boundary. So this then is your outer decision boundary, this is your inner decision boundary, and this in the middle is the surface that we're looking for. That will separate this non-linearly structured data. Hopefully that was clear. If there are questions, please ask. If there are no questions, then I'll move to the next point, which is tuning SVMs, softening margins. So what if I can't come up with a perfect decision boundary? In other words, what if my points are just positioned in such a way that I cannot perfectly separate them with a hyperplane? So what is usually done is you account for a fudge factor that softens the margin if that allows for a better fit. And how do I know that it's a better fit? Well, I would go back to the standard method for supervised learning algorithms. You have to do a cross-validation, you have to do the usual metrics. But if softening the margin allows for a better fit, then that would make sense. So this then calls for hard margin and soft margin. So a large C, which is the tuning parameter, means that the margin is hard. So points cannot lie in it. And a small c means that the margin is soft, so it can grow to encompass some points, although this would not be strictly allowed in the traditional support vector machine format that was first introduced. So how would this make my whole setup look? So the width of the margin will decide how many points can actually lie in the margin. So the optimal value would of course depend on the data set, but if I have a lower value of c, I'm basically allowing for more points to be misclassified. And that then gives me a wider margin and possibly a better fit, but also more number of incorrectly classified points. Whereas I could go for a higher C, stick to a hard margin, and basically come up with a very narrow margin, which would be the typical naive SVM implementation. All right, so that was basically about classifiers. So at this point, I'll stop and take questions if there are any or comments, and then we can go to the next point. You can also unmute and ask if you'd like to do that. All right. So what works for classification also works for regression problems, but with a few important differences. And these are the differences that I now want to highlight so that we can include regression problems in the general framework that we discussed. So my objective now is to consider points that are within the decision boundary line. So what I want to do is define a decision boundary in such a way that I have the maximum number of points that I can accommodate in between. And then given these data points, I'm going to attempt to find a curve. So the idea is the standard idea in regression, which is to find a match between some vector and position on the curve. So ideally, I have points lying on either side, and it is this hyperplane that I'm trying to locate to basically perform my regression. And my decision boundary will be the bounding limits, which will accommodate the maximum number of points. How would this look in a setup? So my task is to come up with a function f of x with maximum deviation of epsilon from the target w. What does this mean? So the points that lie on this boundary here are actually at a distance of epsilon, and they are the support vectors. Not this point, but this point is an outlier. This is measured by another parameter, which is a slack parameter. I'll come to that in a minute. But if you disregard this point and the points here, and instead focus on the points which lie on the boundaries, on the decision boundaries, these then correspond to a deviation of epsilon, the maximum deviation, the margin that we defined earlier. And this has to be set at a maximum of epsilon. And therefore, I want to come up with this line. Modulus of yi minus wi xi should be less than or equal to epsilon. And modulus, because I want to account for both these lines and the points that lie in between. And this is basically what I'm trying to do. In here, of course, b is set to 0. B is your offset factor. If you have b, you can put b into this equation. I just assume that yi is wi xi minus epsilon, setting b to 0. And for a line, this would be a line passing through the origin. I assume that this line passes through the origin. Is this clear? And so these points would then satisfy the condition, and the points lying outside these decision boundaries would not satisfy the condition. And I have to minimize the coefficients, or in other words, the L2 norm, which I already explained, because maximizing the margin is the same as minimizing the norm. And this is basically what we're doing in support vector regression, so that I can have points lying on either side of the line. And this line would then be the line that I'm using for my regression. Line, hyperplane, whatever boundary, but it's a line in this case, in this example. What happens if this is not feasible? In a lot of cases, my points are not going to cooperate with me for me to draw decision boundaries around them. And this takes me to the next point. This data is from a real-world housing data set on Kaggle, and this basically talks about house price in thousands of dollars plotted against number of rooms. As we can see, it's impossible to make the algorithm work for all data points. So what you do is you look for clusters of data points and try and define the decision boundaries there, in which case you have to account for some slack and therefore for another hyperparameter. The slack variable accounts for errors that are greater than epsilon. And what is epsilon? Epsilon is the margin that I described in the previous slide. And so now you'll try to minimize this, of course, the norm of the vector, but also the epsilon I, the errors associated with each of these points. And my aim herein is to make sure that I've come up with a decision boundary that doesn't give too high an error for the points that actually don't satisfy this condition. And now my constraint would then switch to an equation of this form, where along with the error epsilon, I also have to add this error for each of the points. If that is clear, then that was about support vector regressions. And now I'm basically in the final part of my presentation, but possibly also the most interesting part, where I'm going to show you some real world applications and give you a little teaser for what we're going to do tomorrow. And I'm also open to suggestions. I will talk about it when I'm on the slide as to what we can code together tomorrow. So please interact with me in the chat box. Let's quickly talk about advantages and disadvantages, because this would tell you in what situations you can actually move forward and use support vector machines, and in which cases you'd actually be better off with another algorithm. So SVMs work really well where there's a clear margin of separation between the classes. Of course, I mean, that should be clear by now. It's also effective for high dimensional spaces because of the kernel trick. It works really well. It handles nonlinear data easily, and it's relatively memory efficient and quite a robust algorithm in its present implementation. Support vector machine doesn't work too well for large data sets. It doesn't perform well for noisy data where the target classes are overlapping, because it's difficult to define your margins accurately in such a situation. It requires quite a bit of feature engineering. You have to scale your data in order to achieve good results with support vector machines. And because the classification is entirely based on the construction of hyperplanes, you can't really have a probabilistic explanation as to why your data points are categorized in a certain way. And this is probably the biggest disadvantage, at least for me personally, with support vector machines. You don't get an intuitive feel for why a data point is categorized a certain way. Let's talk about some representative examples now. This is directly from the scikit-learn page, and it corresponds to the iris example. I'm sure that the iris data set is familiar. So basically, there are 3 species of flowers which have different petal and sepal characteristics. So you have petal length, petal width, sepal width, and sepal length. And what one tries to do is to use these parameters and classify the different types of the flowers. So these are the 3 types of flowers that I've shown you just to give you an idea for how the data set looks. But more importantly, I also wanted to compare different classifiers on a 2D projection of the data set. Of course, in its traditional form, it's a binary classifier, but you can always do that twice. So once you arrive with the classification, initially, you can further classify within a type to get classification that is non-binary. And that is what is usually done in SVM when you want to have classification of multiple types and not just a binary classification. So linear models will leave you with a linear decision boundary. So you have a support vector classifier with linear kernel, and this is where your boundary is. So depending on your sepal width and sepal length, you have the 3 types shown here. If you have a linear kernel, linear SVC, once again, you get this kind of a linear boundary, which you can see. They look slightly different because the hinge loss function is optimized slightly differently in these 2 cases. And the hinge loss function talks about points that are incorrectly classified. So what margin of error do you allow, and how do you optimize this loss function? If you use nonlinear kernels, which is the radial basis function shown in this figure, you get more flexible boundaries, which gives you some idea as to how you can visualize the classification. Important note, this is a toy problem. Visualizations don't always reflect what is going on with your data. In this case, it does, but when the data becomes complicated in nature with multiple dimensions, then the boundaries that you plot aren't necessarily to be interpreted directly for the data that you have. But in this case, they allow for a pretty decent explanation, and therefore one can easily see that if you move to a polynomial of degree 3, then you have this kind of a boundary that separates the 3 types of iris flowers. Let us move to the second representative example with support vector machines, which is face recognition. So here I've taken an example from the wild data set. I don't know how this is pronounced, but it contains several thousand photos of public figures. And so each image has 62 into 74 pixels. Of course, you can read them indirectly, or you can do some pre-processing. I've basically taken this from the data science handbook from the GitHub repo. Please do have a look if you find this interesting. So what you basically do is you run a support vector classifier, you cross-validate and predict labels for test data. So you have labeled faces in your training data, and you have different pictures corresponding to different people, but a certain number of people. And then you have different pictures, but of the same people as in the training data set, obviously. And then you have predictions that are made based on how the algorithm learned from the training data. And as you can see in this example, support vector classifiers work really, really well. There's only one picture of bush that is classified as Blair that is incorrect, shown here in red. Everything else is absolutely correct. and it works really well out of the box. So image recognition, face recognition is actually an important industry application of support vector machines, as I'll show you in the next slide in a minute. Last example is from a data set from Kaggle. Excuse me, this is not face recognition. This is a data set which is showing you whether a user purchased a product or not based on their age and salary. So it's basically 0 or 1. It's a purchase decision. And depending on their age or salary, one has to predict whether a user purchased something or not. So it's a 0 or a 1, and the only two parameters that you've got here are salary and age, which is a two-dimensional space. You have a training set and you have a test set, and one has to predict the correct outcome for the test set. So the question here is, how would you do it? How would you optimize your support vector classifier? And this is what we had planned for tomorrow. So what I would like to ask you is how you would go about doing this, how you would like me to go about doing this, and also what other example would you like? Would you like to code the points out with me where we can, fit support vector machines from scratch and explore the points, or stick to this problem, or go with the iris data set? I'm open to suggestions. We will take a look at this, but 1 hour is plenty, so I'm happy to work with you on whatever you like and code this out with you. My last slide is on the industrial applications of SVMs for the sake of completeness. Like I mentioned, face detection. I showed you a toy problem, but it's actually used in real life. It's also used for categorization of text, classification of images. Support vector machines have a large number of applications in the bioinformatics space. There are several interesting studies concerning protein folding and remote homology detection with support vector machines. They are also used in geo and environmental sciences. With that, I'm done. Thank you very much for your attention, and I look forward to questions if there are any. Thank you. Over to you, Soham.
Yeah, I think I'm visible now. So there are some questions coming up over there, I think. How to find the optimal epsilon.
Awesome.
Yeah,
awesome.
you can take that.
I'll have a look. How to find the optimal epsilon value. Yeah. So I suppose this question is for the regression, right? With support vector machines. Yeah. So what you would do is you would try and maximize your margin. You would continue to stick to the standard definition and minimize your norm and maximize your margin. And this would then give you the optimal epsilon value. With respect to where you stop and where you allow some points to be misclassified, just so that you have the overall best performance that you can have, would be decided by your cross-validation score and your other metrics. But from the SVM point of view, you're only going to look for optimizing the margin. So support vector machines always work like this. It's a maximal margin estimator. So you always try and maximize the margin, and everything else just follows as a natural consequence. Thank you for the question.
I think that went great. Yeah, we are up for 15 minutes more, and we are up to take up any of the questions that you have. And I hope you guys are participating well on the second task. I think today is the last day for your first task ending, and you guys can hop on to the second task also. So do let us know if you have already tried to attempt the second task, or are facing any kind of issues for the second task. I think many of them are have even completed the second task, and they have gone to the third task. On I think, yeah, there are 15 to 20 people such who have done that. So it's amazing to see like you guys are participating in this. Thank you, Satrupa. All credit goes to Promit. It was really helpful, and some of the things that even I think came to know by today. I wasn't very much aware of it for the epsilon values, that we can maximize the margins and all. But yeah, it was actually insightful for me also. Thank you so much, Promit.
Thank you. My pleasure.
Try to do, but
there's a message in the chat about some problems with the task.
Yeah. Leila, you can let me know where exactly you're facing the issue on Slack, or if there is something that I can do, I'll definitely do, or I can tag Elena. She's the best option to answer all of the questions. Apart from that, we also have the support channel. So you can definitely put up your questions or all the problems over there on support channel. Okay, tag me over there on the question. I'll take care of it. Is it there on the Slack right now? I'll check it right now. 1 second. Have you put it up on? Yeah. Later you can let me know here itself. I can try to resolve as soon as possible. Maybe because I think for Saturday and Sunday they do not work for the Newton AI team. But I think thanks to Ilya that he's already over here hosting it out.
While Soham looks, I'll go ahead and take questions if there are any. So please ask. And if there aren't questions, please give me suggestions for what you'd like to do in tomorrow's coding session, what you'd like to see me code. And I can tell you if there's any preparation from your side so that we can really spend the time together in a productive manner, get some coding done. The only way to learn is to do, and I'm excited to actually code with you. So please interact and tell me if you're joining, what you'd like to see, what you'd like to do, and I can tell you what preparation is required. Maybe even send you something. Yeah.
Sure. I believe for tomorrow's session, the data set that social network ads that you are taking up, right? So I don't think
that we will look at anyway. We will build these decision boundaries and show how it works, play with some metrics. Yeah. But if the participants have any questions regarding it, if they would like to see anything else, I would be happy to hear from them.
Yeah. I think I have something, small project on SVM tomorrow.
Yeah, sure.
We can definitely.
What would you like to do? Would you like to do iris data set? Would you like to just take some points like I showed you and actually map those points onto boundaries? Whatever you like. A little bit of a heads up would be nice because I don't want to code for the first time in front of you, but otherwise I'm open to anything. I'm very happy. Awesome. We can take a look at the iris data set.
That is a good set. Iris is always the evergreen data set, for the classification. And Boston is for
I think Boston is for the regression.
That's the best one for everything. Yeah. I mean, I think what model data set you prefer, Promit, for the learning up on the basics one?
So I've used the California housing data set. That is pretty good as well. That is actually now being recommended over the Boston housing data set because of some ethical issues that have come up with the Boston data set. The iris data set is pretty nice. A lot of commercial data sets are there. Climate change data set is there on Kaggle. That is pretty good as well.
Yeah, breast cancer data set also there.
But the easiest and also an evergreen one is the Titanic data set. It's used for classification as well. Yeah.
Yeah, Titanic is the best one.
Yes, breast cancer data set as well.
I had even practice from there. I started my practice on Titanic data set, and then for the regression I started with the Boston data set. And apart from that, there was Netflix and IPL.
Yes, so yes, as well, indeed.
Yeah,
indeed.
That was the best one.
Yes, Flora, absolutely. We'll map some points as well. That's always fun to do. And yeah, the breast cancer data set is also very commonly used. In fact, there are examples with support vector classifiers there as well. It's also a preloaded data set in scikit-learn.
Yeah. There is this question from Anvesh. Can you take up that?
What is the question?
Is it necessary that the boundary line should be
okay, I see it now. Thanks.
Yeah.
Boundary line should be a straight line, or we can put some curved boundaries also. That depends, on your kind of data. So if your data is linearly separable, then a straight line works. If your data isn't linearly separable, then you'd have to come up with a curve. But the way that is usually done is by mapping it to a higher dimensional space and coming up with a hyperplane in that space and then mapping back their original space. And this is where kernelization comes into the picture. And that's how you actually get this curved boundary. But yes, of course, if you consider the housing data set, the straight line margin cannot be a good boundary. No, it's not. I was actually showing that to illustrate that there are points that are lying outside your margin. And so you need a slack parameter as well. I wanted to make it intuitive that you need epsilon as well as a slack parameter. So you need a width of the margin and you need a slack parameter as well. But to be fair, with regression, there will always be points lying outside your margin, no matter what you choose. But yeah, I took an extreme example to show you how the slack parameter functions.
Okay, I think Leila, I found out your issue over here. I think try to train the same data set for the detail folder. It is called the sales price. Okay, I think Leila, I'll check on this again. I think I have this attention, so I'll definitely check on this and answer to you. This is for the second task. Am I correct, Leila? Okay, perfect. So yeah, I think I can get in touch with some of the Newton people either by today or maybe by tomorrow. If not by tomorrow, they should be working by say on Monday directly. But if in case that happens, that if I get an answer by today or tomorrow, I'll definitely ping them up and see if they can give me an answer by today itself. Okay. Yeah, welcome so much. I mean, that's our job, to help you guys and understand a lot of things. So yeah, definitely I'll get in touch with them by today. I have already pinged them, in fact. So that should be an answer. There should be an answer by today evening. Is there any other question with related to SVM or anything that you would like to ask from it? You can definitely go ahead and ask that.
And also to add to that, if you think of questions at a later stage, you're welcome to contact me as well. You can write to me on LinkedIn. I'm happy to answer, or even on the Slack channel. We are doing SVM on Iris dataset tomorrow. Yes, we are. Somebody asked for it, and I'll be happy to do it.
Yeah, I think then we'll have 2 datasets.
Yeah, we'll start with the social networks dataset, and then we'll do the Iris dataset. And yeah,
Iris dataset is a smaller one, so I think that will take a lot.
Yeah, it's pretty standard and it's established. So you can already see examples on the scikit-learn page. There are multiple blogs written on this, so you can actually acquaint yourself with what's going on. So you'll already have a better idea when you come, and we can then just code it up together. Look at how the data points look, and we can do it together.
Definitely. I think there is another thing I wanted to share with all of you guys. Maybe if I can share my screen. I was just checking out something, so I'll just quickly share my screen. Maybe that should help you guys. So this is what I was checking out today. Sorry, my connection. Just 1 second. Okay. Do let me know if you guys can see my screen. Promit, you can see my screen now?
No, there's nothing visible. Yeah, now it's visible.
Okay. So have you guys heard of this FLAML? What is it called? It's called fast and lightweight AutoML. So this is one of the AutoML library that has been released some time ago, like a month or 2 ago, by Microsoft. So I just sort of, running this out and letting you guys know that this is a very fast library. I was running it right now, and everything is already done over here. Like you can go through the Microsoft page. This is the, the library, or you can say, yeah, the library's GitHub account. You can definitely go ahead and check it out. You can explore this out definitely. I found it very much interesting. So I am, just practicing it out on the accuracy and all those things. So I found it pretty much good. It's pretty much easy, and a lot of things are already done over here. I need to figure out some of the things that are, that this library is providing. You can say, cat boost is available. Then there is light GBM packages. There are Panda packages. There are scikit-learn packages. And apart from this, there is also this, you can say, Plotly is there, Cufflink is there along with this. This can also have the data visualization practices also. So that is also one of the libraries that Microsoft just released right now. So just have a look at it, and I hope you guys can will definitely enjoy it. I'll just share it with you all again on this. Yeah, I think there it is. There's the link. So go ahead, explore this library and see what comes up. I think you guys will definitely enjoy this, because even I'm exploring this myself. So that is definitely something that even you guys can let me know if something that you figure out. Yeah, I think this is very good example that you can definitely go ahead and check on YouTube. I think I just found out from Krishna channel. So that is also something that you can definitely figure out. So I was looking at that. So yeah, do let me know if you guys are able to enjoy this part. Explore it and do let me know what you guys think about it. Okay, it's pretty much new to me also about this library. I am exploring it out right now. So apart from this, there are some of the auto visualization libraries I would like to point out to you guys. Are you guys able to see my GitHub part? Are you able to see my screen, in fact?
No, your screen is not shared anymore.
Screen is not shared. Okay. You should be able to see my screen by now, I think. Do let me know if you guys can see my screen now.
Yeah, it's visible.
Yeah, it's visible now.
Okay, all right. Yeah, just 1 second. I want to show you something. Yeah, meanwhile, Promit, can you share your LinkedIn ID on the chat?
Yeah, I'll do that.
Yeah. All of you guys just have a look at this particular project that I did sometime earlier. You should be able to find out this Netflix EDA that we did. I mean, this was a practice we were doing while going up through the course and all. So this was just a practice. I was curious to learn a lot of things. So have a look at it. This has 3 particular libraries that is called SweetViz, that is Sweet Visualization, complete form is it. Then we have there were other 2 libraries also. 1 second, I'll just scroll down, show you over there. That is yeah, this is the SweetViz library that we have. You can definitely go through the code, and there is the SweetViz page already available, so you can check out on the Google also. Yeah, this is a link for SweetViz. You can go ahead and explore that. It is very beautiful library. You can a lot of auto visualization is completely done over there, and this will give you a new link to it, so you can definitely enjoy this also. Okay. Secondly, there is another library that I have done over there is there is AutoViz. Okay, so you can also explore this part. I won't tell you a lot about AutoVis right here, and you guys can definitely explore this on your own as well. So there are a lot of visualization techniques that have been done. You can see Matplotlib, you can see stats model, you can see XGBoost, you can see scikit-learn, and the Seaborn, Prom, Pygments. I'm not sure. I haven't used that library ever, but yeah, there are a lot of things going on here. So you can definitely go ahead and check it out. Third library is my favorite. I'll show you right now. Is detail. This is my favorite library. This is because detail gives up a complete analyzation, and it gives you to analyze on your own. You can give everything on your own. Like I have to run up this particular code somewhere and see, because if you see this particular link is where you need to copy paste. I think I can give it a try. It should be there ideally. Yeah, it's an error because the file is no more active. So yeah, you guys can definitely run up the complete code yourself and check it out. This library has a lot of features. I want you guys to explore it and tell me which one is the favorite of all of you. So I'll just list down the libraries over here. That is SweetWiz. Then there is AutoVis, and then there is detail. So go ahead, check it out. You can explore more such libraries and let me know which one is the favorite of yours. So this should help you guys to auto visualize and all. So that's it from my end. I hope this should definitely support you guys, help you guys about something. So yeah, do let me know if you guys have any questions for Promit, from me, from Palla, from Namita, from Anu, anything, and we are always here to answer everything for you guys. Yeah, thank you, Satrupa sir, thank you, Leila. I think I have another option. Yeah, sure. There are some of the questions popping up on my Slack that are very much related to the task. If you guys have any other questions with related to the task, or you can say with related to any of the algorithms that you are going through, or any of other doubt apart from just the algorithm that we are covering, even that we can definitely try to cover up and answer you guys. These links to the task. Or didn't get you, Vasavi? Okay, can you repeat that question again? I think you want to share these links on Slack. Okay. Yeah, I'll definitely share these links to Slack. Yeah, for Promit's LinkedIn ID, I'll share it on Slack. I'll share my GitHub ID on Slack as well. You can definitely go ahead and check it out. And yeah, I think all these libraries are also there on the Slack. I'll share all of it on the Slack after this session. So any other questions you have, we are up for it. 5 minutes more. Oh, I think no questions. Promit, you did a very good job, I think. Okay, if you guys have no questions, then I think we can end up the meeting over here, end up the sessions over here. If you guys have anything in mind, if not by now, by today, tomorrow, and anytime, you can ping us on Slack, on LinkedIn also. Okay.
If you're pinging me, then please stick to LinkedIn because I'll see it faster and I can respond before the session. Yeah, thank you, all of you.
Thank you, Anvesh. Thank you, Promit, for wonderful sessions also.
Most welcome. Thank you for having me.
Thank you so much. Thank you, Ajal. Thank you, everybody. Have a great day.
You too. Bye-bye. Bye all. Have a great day.